Hello and welcome to our paper presentation for Team 7. For our paper presentation, we chose to review the following paper, Digital Forensics, the Next 10 Years, by Claudio Casas, Armando Capote, Claudette Fernandez, and Jose Paguagua. The paper that we chose to review is called Digital Forensics Research, the Next 10 Years, and provides an outlook for digital forensics into the future. The paper that we chose to review begins by going over some of the major hurdles that digital forensics will have to overcome in the following years, and technology landscape continues to grow in complexity and usage, and then goes on to propose a plan in order to improve digital forensics and the processes behind it in order to keep up with that growth in a meaningful manner that will still provide the assistance and results that have come to be expected from digital forensics professionals and departments. Some of the major hurdles that are proposed in the paper include the following: an increase in density of device deployment. Some of the major challenges associated with this would be to reconstruct physical events on the basis of unevenly deployed devices. For example, not all the space has the same density of Internet of Things nodes and information. This can also vary according to the considered environment. Device types. The challenges behind device types are to provision a computer-aided, evidence-driven, and court-proof frameworks for the reconstruction of events. Such software should be able to take into account a mixed, increasing set of devices, for instance, by means of a plug-in architecture. Another major hurdle is the lack of specific device location. A cost-benefit analysis to determine whether Internet of Things devices located in hard-to-reach areas are worth accessing. One idea is to use databases that point out device properties useful for forensic investigations and additional details such as the accuracy of onboard sensors. This influences physical accessibility of the device for a digital forensics investigation. The device might be placed behind country borders, and influences which area of physical environment was covered by the device, the part of a forensic site that has been influenced. Another such hurdle would be recording history. All available information on IoT devices can be recorded locally or in the cloud. Local storage is usually limited, thus, the number of recorded sensor values, actuator states is kept under a certain threshold. Older data might not be accessible. Therefore, automatic integration of IoT devices into the reconstruction process of physical events is necessary. This requires fetching the recording history of sensors and correctly placing it within time frame of the event to be reconstructed. It could entail the support of visual analytics tools capable of handling devices that provide data with inconsistent or inaccurate timing and spatial positions. Device interfaces. The interfaces used to access evidence highly influence the amount of information that can be retrieved. Some types of information might not be provided by certain interfaces, while others are. In several cases, interfaces might be undocumented by the vendor. In order to meet this challenge, we need to provision a unified meta interface for IoT forensics covering a large spectrum of different devices and low-level interfaces of several vendors. This can likely be adequately addressed by larger community projects. One very important example that was proposed by the paper that we chose to review would be digital forensics for law enforcement. Digital forensics is an important tool for solving crimes committed with computers. For example, phishing and bank fraud, as well as for solving crimes against people where evidence may reside on a computer. There are two fundamental problems. Today's tools were designed to help examiners find specific pieces of evidence, not to assist in investigations, and today's tools were created for solving crimes committed against people where the evidence resides on a computer. They were not created to assist in solving typical crimes committed with computers or against computers. The prototype DELV, which stands for Distributed Environment for Large-Scale Investigation System, described and illustrated in the accompanying figure, uses these principles to achieve substantial speedup of forensic operations, even when using only a limited number of nodes. The availability of abundant CPU resources allows the creation of very responsive tools, allowing an investigator using DELV to issue many parallel queries and see results as they become available, rather than using a sequential query response query model, as is more common in current generation tools. To date, experiments with DELV show speedups well in excess of the concurrency factor for I/O-bound operations and nearly linear speedups for CPU-bound operations, such as stenography detection. More work is needed on an effective user interface for DELV, on fault-tolerance facilities for handling node failures, and on plugin architecture for incorporating and parallelizing existing sequential tools. With the ever-growing technology landscape, new forensic research directions are necessary. One such example is forensic data abstractions. Today, there are only 5 widely used forensic data abstractions: disk images, packet capture files, file signatures, and extracted named entities. Efforts to develop new formats and abstractions have largely failed. The digital forensics community specifically needs to create a wide range of abstractions, standardized ways for thinking about representing and computing with information ranging from a few bytes to a person's lifetime data production. For example, some such data abstractions would include the following: signature metrics for representing parts of files or entire files, including n-grams, piecewise hashes, and similar metrics. File metadata. Microsoft Office document properties, JPEG, EXIF information, or geographical information. File system metadata. For example, such as timestamps, file ownership, and the physical location of the files in a disk image. Application profiles. For example, the collection of files that make up an application, the Windows registry or Macintosh plist information associated with an application, document signatures, and network traffic signatures. User profiles. For example, tasks the user engages in, which applications the user runs, when the user runs them, and for what purpose. Internet and social network information associated with the user. For example, the collection of accounts that the user accesses, or user internet imprint or footprint. Similar to the lack of standardized data format is the lack of standardized architecture for forensic processing. Today, forensic software is largely developed in C, C++, Java, Perl, Python, and guidance software's proprietary NScript language. The software is run on Microsoft Windows, Apple Macintosh, and Linux operating systems. Faced with such diversity of development choices, other developer communities have created frameworks that enable cross-language, cross-platform development. Typically, these frameworks include standardized processing models, cross-language APIs, and straightforward data marshalling. Some of the best examples of such framework include the Apache Web Server Module System, the Mozilla Firefox web browser, and the Eclipse development platform. No such framework exists for processing digital forensic information. For example, a framework might allow plugins for file systems, processing of sectors, IP packets, byte stream objects, timestamps, email address, proper names, and so on. The framework could have a variety of correlation subsystems, including an object-based hierarchical store and temporal events database. The output subsystem could allow any plugin to emit structured data. This data could then be used for textual reports, interactive reports, visualizations, or to drive some kind of automated event system. Scale is an important issue to address early in the research process. Today, many techniques that are developed and demonstrated on relatively small data sets do not work and fail when they are scaled up to real-world sizes. At the same time, researchers are failing to develop a range of techniques that don't work at a small scale but perform quite well when run in a data-rich environment. For this reason, researchers must have access early in the development process to realistic large-scale data sets. Given the ability to treat collections of data and metadata as self-contained objects, and to treat advanced forensic processing across multiple drives and data streams as simple function calls, researchers will be able to move up the abstraction ladder. We will then be able to create a new generation of forensic techniques, tools, and procedures to help address the coming digital forensic crisis. Challenges posed by cloud computing technologies for digital forensics. The organizations are now able to manage and deploy their infrastructure in remote, virtual environments that are many times managed by third parties instead of having to physically procure them. This expansion has had very important and significant implications within the digital forensics field. An investigator may be faced with gathering an extremely large amount of data placed in a cloud by a user. One solution investigating authorities could resort to is the use of public clouds to store evidence. This too will bring its own challenges for both legal and technical perspectives. Investigators will need to address the rules and regulations regarding data protection and privacy issues and their impact on evidence stored in the cloud. Digital evidence issues. Some of the digital evidence issues that we have come across are tools. A critical problem in the uptake and acceptance of new forensic tools is the expense of producing high-quality test results. This has the consequence that tests and evaluations are either few and far between or to some extent informal, which undermines their assurance. Embedded systems. The challenge is to keep apace with the new devices by developing the necessary tools. New consumer products with embedded logic and data recording capability, like having potential forensic value, in some case for the organization selling the product, but also for the forensic investigator. Data volumes. New scenarios of interest as storage locations increase. Frequent patterns of behavior are also recorded on these large data storage systems. Infrequent patterns of behavior anomaly detection is also important. The real challenge here is to find data mining techniques that are scalable. The Integrated Digital Investigation module does well at illustrating the forensic process and also conforms to the cyberterrorism capabilities, which require a digital investigation to address issues of data protection, data acquisition, imaging, extraction, interrogation, ingestion/normalization, analysis, and reporting. It also highlights the reconstruction of the events that led to the incident and emphasizes reviewing the whole task, hence ultimately building a mechanism for quicker forensic examinations. The Enhanced Digital Investigation Process model is an enhanced version of the Integrated Digital Investigation Process model and seeks to redefine the forensic process and its progression. It describes the development right from the point when the initial infrastructure is put in place to investigations when the incident is reported through the traceback phases that would lead to the point where the crime was committed, and finally to the ultimate investigations that would lead to conclusive results.